So, we at our last topic. We're talking about graphical models. What are graphical models about? Typically, use graphical models to describe probability distributions or more general functions of many variables that are non-negative. And so the typical case are probability distributions by describing them in a graphical way. So variables, for example, are nodes, and describing some local interactions, some local rules that they have, and the whole thing describes a probability distribution. There are many, many different graphical models. What we're talking about is one, BaseNet. And these many languages, and maybe at the end I'll mention a few, can be used for various different purposes. So for example, BaseNets are nice to describe independence relationships and some other things. But there are many other models. So for example, factor graphs are nice to do algorithmic things like computing marginals. And Markov random fields have, again, some other use cases. Okay? So unfortunately, through historic and through that many areas used to be independent, many such different models were discovered. They're kind of often similar, but not exactly the same. So it can get quite confusing, but you will likely gonna see many different such versions, if you stay in this field. Okay, so let's now go back to BaseNet. BaseNet. So what we said is the intuition or the motivation really comes from the chain rule. So you have something, a distribution, maybe depends on 4 variables. And so now there's the standard factorization, the standard chain rule that you can write down. And so we associate now to each of these x1, x2, x3, x4 a node, and then we draw so we're having a node for each of this. This is x1, x2, x3, x4, and we draw a directed edge if something influences it, right? So px1, there's no edge into it. Px2, there is one because it's in the conditioning of the x2, and then we're having these extra nodes here. This goes to 3. And this goes also here, and this goes here. Okay, and so we said that, okay, there's of course, in general, if the dimension is d, then in general, d factorial ways of writing it down. And this is completely generic. And if it was just like this, it wouldn't be very interesting. It becomes interesting, and we can then say interesting things about distributions if we're not talking about generic distributions, but if in some of these conditionings, some of these variables are missing, which means some of these edges are missing. Then things become interesting. And so we asked the question, which directed graph corresponds to a probability distribution to validate such factorization? And we said that this corresponds to what's called DAGs. Okay, directed acyclic graphs. So if it's acyclic, then it does correspond to a probability distribution. So remember what it means to be acyclic. It means that you cannot go in a path that closes up on itself in the direction of the graph, in the direction of the edges. So any directed acyclic graph does correspond to some such factorization with possibly some of these children missing, okay? Or sorry, parents missing in the thing. Good, so now what we want to do is I want to draw a graph. Maybe it's going to look something like this. Maybe something like this. And so maybe I have something like this. Right? And so we see that, that compared to what I've drawn here, there certainly some of these edges are missing. And so now I want to ask certain questions, right? So I want to ask, for example, is x1 independent of x3 for example, given x2. Okay, so this is our notation, x1, and that's a question. Okay, so the question is, I give you this, and I ask, is x1 independent, it's like, looks like orthogonal, independent of x3, conditioned of x2. So someone gives you the value of x2, now you still have the random variable x1 and x3, and you want to know whether just from the pure structure, just given that this is the structure of this distribution, not knowing anything else, whether that, for any distribution that's compatible with that structure, these random variables are independent. Okay, so these are the kind of questions that we would like to answer. And so generically, we'll be able to answer much more general questions. So it will in general not just be a single random variable, but there could be a whole group of random variables, a whole group of random variables, and there can also be a whole group of random variables. Okay, so these are the kind of questions that will be answered. And so the way we do it is that we're just looking at 3 very simple examples. And these 3 simple examples will kind of tell us the basic dependence and independence relationships. And from that, the general statement more or less follows directly. Okay, if you're just looking for some extra motivation, it's the last lecture of the last course. Okay, this makes for great exam questions, okay, because there's infinitely many such questions in graph I can draw, okay, and I can ask any kind of graph and then give you any kind of random variables and any kind of things. Okay, once you understand it, very easy, okay, but don't tell anyone else, okay, it's just for you, okay, good, okay, so good. So what are the 3 examples? The 3 generic examples are like this. So the first example is this. So I have x1, I have x2, and I have x3. And so I have that relationship. So I have only something with 3. And so this means I have a p of x3, right? And then I have p of x1 given x3 times p of x2 given x3. Okay, so this will be one example. Then we'll have another example. It's always just 3. I have an x1, I have an x2, and I have an x3. And so this will mean the distribution here is p of x1, p of x3 given x1, p of x2 given x3. And the third one will be this. And so this means it's now p of x1, p of x2 times p of x3 given x1, x2. Okay, so I hope that number one, forget about this, I hope number one that this thing here is clear what I mean, right? Given this graph, what is the distribution, what is the form? Well, I have to start with something that doesn't have something coming in, right, as a source. So I have to start with x3, for example, that's the only source here. And then I have 2 factors, right? The x1, the only parent it has is x3, so I have x1 with its parent. And then I have x2 given its parent. Same thing here, right? I have to start with a source, something that doesn't have anything coming in, p of x1. Then x3 sees x1 as a parent, x3 given x1. And x2 could depend on x3 and x1, but since there's no edge coming here, it's only x2 given x3. There's no x1 in here, right? And the same example here, I have x1 and x2, and now the two errors go up. So I have 2 possible sources, x1 and x2. They don't depend on anything. They don't have any parents. But x3 has then parents x1, x2. So right now I've not said anything. I've just given you 3 scenarios. And now we want to look at these 3 scenarios and want to understand to what degree these things are dependent or independent. So far, so good? So let's see. Let's start with the first example. What we're going to be interested in is always in x1 and x2, and we're going to ask whether or not it's independent or if it is independent conditional on knowing x3. Right, so I'm going to ask, my question that I will always ask, maybe let's write it there, so it's not so far away, and we think of the first example. So we're asking, is x1 dependent or independent x2? And we're also going to ask, is x1 independent x2 given x3? Right, so let's first answer the first question. In the first scenario, are x1 and x2 independent or dependent? If I give you something like, so when we're asking this question, the sense is the following. When I'm saying are they independent, I'm asking, given this structure, is every distribution that is compatible with the structure such that these two random variables are independent? Right? Even if I have this structure, of course, I can still pick, this simply means that in principle there's a conditioning in there. But of course, I haven't said what exactly this function, I can pick whatever function I want. Right? So the sense is every distribution, for every distribution that has this form, are x1 and x2 independent? Or could you construct some for which these two were dependent? Right? Because I haven't told you exactly what these factors are, right? There's still a lot of degree of freedom in there. Sorry, in the first, yeah. So x1 and x2 are clearly dependent, right? I mean, you have the parent, and the parent dictates, something both. I mean, it's pretty clear, right, that in general, this distribution will, will depend, right? So depending what you pick on the x3, right, the x3 can influence both of the x1 and x2, and it's clearly easy to construct something where these two could be completely correlated, right? Okay, good. So now what happens? So this is no. Okay, so in general, these things will be dependent. But now what about here, right? So let's check. So I have whatever I have here, P of x3. So what I'm asking, so does it mean to be conditional independent? It means that x1, x2, condition on x3 should be, and that's the question, is that equal to P of x1, x3, times P of x2, given the x3 here. Right? So, but what is this, right? So I have here this is P of x1, x2, x3 over P of x3, right? That's just generically by Bayes' law, right? So the conditioning is just this. Now I plug in what this thing is. This is P of x3, right? So I know what this is. P of x3 times P of x1 given x3 times P of x2 given x3 over P of x3. Right? So all I've done is now plug in on the top for the joint distribution this particular model that I have, right? So we see that indeed this is x1, x3 comes P of x2 given x3. Okay, so this means indeed conditioned that I know the value, okay, of the x3, these two things will be independent. Is it clear what I did? Okay, so the important thing is that what you want to show is this. You write this down generically as this. You plug in whatever the model tells you. And now you try to see whether you can bring it to the form on the right. Right? And that's it. So this means the following. When in the future I'm talking about a path, I mean an undirected path. Okay? So it means the following, so we have a path here between x1 and x2, which might in general be worrisome because somehow this indicates that there's some relationship. But if I tell you what the value of the x3 is, And I'm in this scenario which is called, it's the, in this scenario here where you go, where both of them start at x3, okay, then indeed that blocks, the knowledge of x3 blocks this dependence. Okay, so this will be the first, yes?
So for the first one to be true, the x1 is dependent just of x2. It means in the graphical manner you would need two elements that are not linked by any directed edge.
It's very special, right? Look at the first and the last case. They look more or less the same, but it does, all three cases are the same, but they depend on the direction of the things. So it's more subtle. It's not just that there's no path, so it depends whether it's like this, like down, or like this. Okay, we'll talk about all three cases. These are the three generic cases, and we'll see that the answer is not always the same. Okay, but for this case, if you look at that picture, okay, it's the same. Yes?
The first model, because you always say looking at this case, but you don't...
No, the first, I mean...
So the first one?
No, so we have three cases, right? 1, 2, 3. I'm starting in the standard way, reading left to right, okay? And top to bottom, okay? Let's clarify this once and for all, okay? Good. Okay, so far so good. So now let's check what happens for the second case. And again, we'll ask exactly the same. And well, this is still exactly the same, right? So we ask this question, and now we want to do the same. We want to do the same thing, right? So generically, for the first question, are x1 and x2 dependent or independent? Generically. So it means, can you construct a distribution that follows that general structure where x1 and x2 are dependent? Right? Sure, right? I can clearly do this, right? Because I could take x1 to be equal to x3 to be equal to x2, right? I pick x1, that influences x3, right? And then x3 influences x2, and they could all be the same, right? So they could be identical, right? They could be as correlated as you want to. So in general, right, this will be, again, no. For this case, no. Okay, so this is not true. So generically, these two things are dependent if I have a structure like that. Okay, so let's look at this again, right? So what do we have here? So we have again P of x1, x2, x3 over P of x3. And now we want to plug in again what we have, right? So we have the distribution P of x1. Then we have P of x3 of given x1, and then P of x2 given x3. And now I'm trying to see if with generic manipulation, knowing nothing else, I can show that this indeed is the right-hand side, right? So this thing here is just the same thing as the joint distribution P of x1 and x3. Right? This was just the factorization of the joint distribution generic. But now what I can do is I can take out the P of x3. I can write it the other way around as P of x3 times P of x1 given x3. Right? So I can write this as P of x3 times P of x1 given x3. Right? I had it just the other way around. I had it as P of x1 given x3 given x1. I write it now the other way around, right, as P of x3 times P of x1 given x3, right? It's completely generic, not used anything, right? But now, of course, I can again cancel, and this thing is exactly this, okay? So it's exactly the same, result that we had beforehand, that unconditioned, in general, these are not independent, x1 and x2. If we're talking about a chain that goes along with the errors being aligned. But if I give you the value, or if I tell you the random variable in between, then that blocks this dependence between the two, right? And now conditioned, these two things actually will become independent, and that's again generic, okay? It has nothing to do with the specific functions that I pick for these things. Okay? Good. So let's try the third thing, right? So let's try now the third one. So now it becomes dangerous because we have twice a setup and it's twice the same result, okay? So we might get complacent and think it always works like this, and boom, okay, just when we get there, turns out it's wrong. So let's look. For the last one, what do we know about x1 and x2? Are the two dependent or independent? They're independent, right? Because I have p of x1, p of x2. If I want the joint distribution also with the third one, then I have p of x3 given the two. But just the distribution itself is x1 and x2. They're both sources, right? They're both, none of them influences anything, right? So now, they're actually independent like this, okay? But it's not very hard to see that if you now make them dependent on this, if you now give me the x3, right? If you condition on the x3, then you make both of them dependent. Is it kind of clear? Just think of a scenario, whatever. I guess in the notes have something like you are, let's say x1 is x1. Let's assume they're all binary. x1 is that you are x1 takes on the value 1 if you're super smart, okay? x1 takes on the value 0 otherwise, okay? x2 takes on the value that the exam is, let's say, is 1 if the exam is difficult or is easy, let's say, okay, and 0 otherwise. And let's say x3 is that you passed your exam and you got a grade of 6, right? So either 6 or something else, right? So now clearly, if I condition, depending on what the exam is, right? You can see that of course these probabilities in general, a priori, these two things, whether the exam is easy or difficult and whether you're smart or not, these are completely a priori independent random variables, right? But if I tell you something about the outcome, things might actually change, okay? And there's actually something in a phenomenon that you sometimes might hear, it's called explaining away, okay? Explaining away is the phenomena that if you have that, so, you have these things, maybe originally these two things are independent, and, so you have this thing. So now I give you the result of that you passed the exam, okay? So now actually you create some dependence between the two. But if I now tell you in addition, let's say if you have in addition some side information, for example, that the exam was easy, okay, or that you have something that explains already why you might have passed the exam itself, now suddenly, whether or not you're smart or not, that question again becomes, there's essentially no influence again, because already this side information that he gave you was enough to explain away the result that you have seen. Does this make sense? Okay, so you have a priori was independent, then I give you this, might actually become dependent, but now if I give you some extra information, you have some extra side information about one of those that might already explain why certain things happened, the outcome happened, then the rest suddenly again, basically you have no, it doesn't give me any particular knowledge about the original, let's say, the original question that I was interested in. Okay, it's just something that you might hear once in a while. Okay, so now we have these three scenarios, and so they have funny names. So I think this is called the names themselves are not so super important. This, I guess, is called here, so this is called tail to tail because this is the tail and this is the head of the thing. So this is called, sometimes here this, then sometimes you hear here head to tail, because you have here the head and have the tail, and this would be head to head. Okay, so now it turns out that essentially that's all that ever happens, okay? Anything that will now, you know, for the more general case, can all be explained by looking at one of these three scenarios. It just will be slightly more general. And so given a DAG, so remember, DAG is just exactly one of these graphs that we have, okay? So given a DAG, the set of, you know, random variables x. So I'm thinking, I'm just writing here x, but x might be a whole collection of random variables, okay? It might not just be a single one. The set of random variables x is independent of, and again, this could be a set of random variables y given, and again, this could be a whole set of random variables c if every path from x to y is d-separated by z. Okay, so it's one of these definitions where we'll have to write down 3 statements until we get to what we actually mean. So it is, or maybe you should write if, sorry, this is not very good. If, sorry, let me write it down, is if x is d-separated by c, if x, maybe, and y are d-separated by c, it is every path from x to y is d-blocked. Okay, just hold on. It will turn out to be not very difficult. It's just more writing. Okay, so I give you a DAG, and we'll do lots of examples, so don't worry. I give you a DAG. Now I give you, let's say in the simplest case, one random variable x, another random variable y, and a third random variable c. And I ask, is x independent of y given z? And this will be true if the following is true. If for every path from x, from any of the elements of x to any elements of the y, if you go along the path, and path here I mean not a directed path, just a path, it is true that there exists on this path a variable, let's call it u, such that one of the following conditions hold. And these conditions are exactly these conditions that we worked out here. Okay, so the condition that worked out here, remember, x1 and x2 were dependent, but as soon as x3, which is now this random variable that's on the path, as soon as I get to tell you what it is, and that's meaning the conditioning, they were independent. Okay, so that's one way to block a dependent path. Another to block a dependent path, if I have this x1, x3, x2, so the head to tail scenario, again, if I can find on this path somewhere a node where it's exactly the two, you know, it's head to tail, these two things are aligned, and in the z, the x3 is in there, so I tell you what the x3 is, then again, I block the dependence that's inherent in this path. Or, if I have x1, x2, and somewhere in the path there's an x3, and I have now the head-to-head scenario, okay? But now, this x3 should not be in the conditioning, okay? Because if I put the they're independent, as we said, but if I put the conditioning in there, they are no longer independent, okay? And so these conditions are exactly these three things. For every path, there has to be one of these three cases, at least one of these three cases has to be there to certify that this influence that this path has, a priori, is blocked, okay? And it will be exactly these three scenarios. So let me write it down and then we'll do lots of examples. So that, okay, U is, so, wide. So we had U is tail, tail, and U is in Z, right? Or U is head to tail, and U is in Z. Or U is head to head, and neither U nor any of its descendants is in C. Okay, so let's just see. So U is tail to tail, that's the first scenario. And then the x3 better be in this C. That blocks the influence. Second one, right, we have head to tail. Then there's something in there in this path. The path can be much longer than just, length 2. This could be a long path, but somewhere in between, there must be something that looks like the scenario x3. And now again, the x3 has to be in there, and then that blocks the influence. Or it is somewhere along the path I have something like the x3 in the final thing. But then this better not be known because that would actually introduce dependence. And okay, I didn't mention it before, but if x3 had a child, okay, so there would be something going out there, right? Had a child, and I would not know the x3, but I would know that child, then again this introduces dependence, right? Because I could always pick x3 and I could identify it with the child and I could construct a distribution for which I introduce dependence. Okay, so these are exactly these three cases that we have here. Okay, so now the easiest thing is just to do many examples. It looks more complicated, it's actually not very complicated. So let's go through some examples. We have quite some examples in here. So let's see. So we are now looking at this one, this one, okay? And I'm asking now questions about this example here. So let's say x1 is independent of x3 given x2. Let me just make sure that I drew it in the same way. I think I did. Okay, I want x1, x3 given x2. So is x1, does x1 and x3 independent if I give you the x2? Okay, so what you have to do is the following. In this case, it's simple in the sense that the x1 and x3 are just really single random variables. Okay, all these things still applies if x1 was a whole group, the other one was a whole group, and then I would have to look at all possible paths going between all the elements of here and all the elements in here. Okay, but now it's easy. I just give you one random variable, one random variable, one random variable. So now ask x1, x3, x2. So how many paths are there between x1 and x3? What do you say? 2. What are the paths?
x1 to x2, x2 to x3.
Okay, that's how long the path is. But
Oh, okay. So x1 to x3 and x4 to x3.
no, just between x1 and x3. How many paths are there? You start in Lausanne, you want to go to Bern. How many paths are there? 1. Okay, and that path is just x1, x2, x3. Okay, that's the path. And you know, path here, I mean, it doesn't have to be, you know, it's not a directed path. Okay, in this case, it is a directed path, but in general, it doesn't have to be a directed path, right? So now, for every such path, I have to find you one of these. I have to find you one of these reasons, right? If for every such path, I can check that one of these conditions, at least one of these conditions, is true. Then this will be conditionally independent. Right, so let's check. Is there on this path a variable u, right, which is in z, in the conditioning, and u is tail, tail, tail. Is that true? I mean, the only variables I have on the path, right, that is not the x and not the y and the thing, is just right now the x2, right, that indeed happens to be in the conditioning, right? But, you know, that's not true. It's not tail to tail, right? Is that true? Okay, so for this one, this is true. And since this is the only path, indeed, that is conditionally independent, right? And so I think, you know, you can see already, this is still a very simple example, but you can see already that it might not be completely trivial if I wrote you this down now with the conditioning, right, like what we did beforehand. You know, you might have already many ways to check whether or not this, you know, what you want to do is correct, right? And it's easy to write you down something with 20 nodes and 3 conditioning, and it might not be so easy to do this, you know, just the standard way how we did it before. So that's a useful thing to know. Okay, so indeed, this is correct. Okay? Okay, now, is it true that x3 is independent of x1 given x2? In other ways, it's symmetric, right? There's, of course, this is a symmetry relation. If things are independent, you know, there's no, neither, you know, the first and the second argument play no special role. This condition, this property is symmetric, right? So obviously that's also true. Of course, we could check again, but it's of course true for exactly the same reason, right? In these paths, you know, I'm not talking about that the path has to start in x and then, you know, if I have a path here, then I also have a path backwards, okay? You can see also that all the conditions are, of course, symmetric. Good, so let's see. What about x3 and x1? Oh, this is the one I have already, sorry. What about x4 and independent of x1 given x2? Okay, is x4 and x1 independent given x2? So how many paths do I have between x4 and x1? Exactly just one path. Now, are they independent or not? Right? It's exactly the same reasoning. It's a path. Now the path is a little bit longer, but it's still x2 blocks this, right? So the second condition is true. So perfect, okay? Okay, let's see. Do we get anything more interesting? Okay, let's try maybe x4 and x1 given x2. Oh, sorry, given x3. Okay, so now instead of giving you x2, I give you x3. And? Shall we vote? No. Right? Because, you know, so there's only, let's look, right? So for the x2 to be blocking, I would have to know it. That's the second condition, right? But that doesn't apply. So x2 cannot be the variable. And then the only one then is x3. And for x3 to block, I would have not to know it in any of its descendants. But unfortunately, I do know it, so the third one doesn't apply either. Okay? So none of them applies. So this means there's an easy way to, and we'll talk about it in a second, to construct an example for which these things are actually dependent. Okay? So this is whatever. Wrong. This is correct. So what about x4 and x1? Is x4 and x1, are they dependent or independent? So which one applies? Right, the third one applies because now x3, that's the head-to-head situation. And if I don't know that and none of its descendants, right, then that blocks things, right? Also easy to see, both of them are sources themselves, right? So I can just write down the distribution as P of x1 times P of x4, and then the rest is just the other ones, right? So they're clearly independent. Okay, so in the notes I have, some other examples. Let's not go through them now, but I can almost guarantee you that some of these examples you will see, okay, again in your life, and maybe very soon, okay? So, okay, good. Okay, that was the fortune cookie, so let's see what else we should do. So there's one thing that one has to be a little bit careful. When you have in this model, when you have these errors, then it's tempting to think of them as causal relationships, right? So it's tempting to think about, if I, for example, have this, that I have x1, and then x1 causes x2, or whatever the effect of x2, etc. Okay? Now, we have to be very careful with this, because we have seen that generically, if I have, let's say, just p of x1 and x2, right, then generically I can write this down as p of x1, p of x2, given x1, and so the graph for this would look like this, x1, x2, like this, right? But of course, generically, I can also write it down as p of x2, p of x1, given x2, right? And so this means I have x2 and I have x1, and now it looks like this. Okay? And so this is completely generic. We have not said anything about what causes what or what is this. And so this might look that in the first case that x1 somehow causes x2, and the second one might look like x2 causes x1. Okay? So these errors have nothing to do with causality. Right?
So doesn't it create a problem between tail-tail and head-head? Because the only difference between them is the which way the arrow is going.
All I mean is if you, whatever, you're saying smoking, maybe one of them is smoking, the other one is cancer, okay? If I drew maybe the left hand x1 was maybe smoking and the right one was cancer, and I draw that, okay? Then you might, maybe someone might conclude saying smoking causes cancer, okay? Might be true, but it has nothing to do with this representation, okay? Because you could also do it the other way, okay? You could also say cancer causes smoking, okay? If you draw it the other way around. Clear? Okay, so be careful. That's just a representation, and errors have nothing to do with causality. Of course, there might be causality, right? But there's nothing to do with that particular representation. Okay, so there's still two concepts that I want to talk about after the break. One is something called the Markov blanket. It's something fairly easy. And the second one is maybe talk about then computational tasks that you might want to do, like marginalization or sampling. We'll just mention it, and I might mention a few other possible graphical models, but let's enjoy first a break. Okay?